At Netflix, 500 billion events and 1.3 petabytes of data are ingested by the system every day. This includes video viewing activities, error logs, and performance events. On today's episode, we dive deep into the data pipeline at Netflix and how it evolved from the 1.0 version to the modern 2.0 version. The idea for this show came from a blog post on the Netflix tech blog called The Evolution of Netflix's Data Pipeline. So I encourage you to search for this article and check it out either before or after this episode. And before I get to this episode, I want to take a quick second to explain how the pipeline works, how the evolution has worked. So the 1.0 version had event producers like your device or really any type of action on Netflix's infrastructure that produces an event that Netflix wants to log and perform analytics on or do some kind of response to. So every event got produced and put into this event collection and aggregation platform called Chukwa. And Chukwa was kind of this point where the events were stored in Amazon S3 and you could do MapReduce jobs over all of the events that were stored on S3. So this was very simple. This was the 1.0 data pipeline. Just all the events, all the data on Netflix got thrown into Chukwa on S3, and you could run MapReduce jobs on them. So this was a very batch-oriented event processing system. So as they were going towards the 2.0 version of the data pipeline, they had an intermediate stage where they re-architected to have an additional branch off of this Chukwa event data collection storage system. And this additional branch had Kafka, and Kafka was used with a routing service that they built, and you could do stream processing off of those events. So this was kind of like they just forked this original pipeline that was just doing batch processing. And in the 1.5 version that I'm talking about now, the event collection and ingestion process was kept the same. And they made it so that all the events also were available to do stream processing. So many early episodes of Software Engineering Daily were covering this movement from batch processing to stream processing. And this episode really epitomizes and collects a lot of the discussions that we had in those early episodes into a real evolution of a architecture that has gone from only focusing on batch processing to something where it's really stream processing. So this intermediate stage where they forked the event pipeline to also have stream processing in addition to the batch processing, this was what they called the 1.5 iteration of the pipeline. And then they moved on to the 2.0 version of the pipeline. This was a even more re-architected platform to have more real-time access. And in the episode, we go through all this. Stephen Wu is the guest. He works on the Netflix data pipeline. But this 2.0 version, just to give you a quick summary, and again, I encourage you to check out the blog post to have some insight into how this actually works. Maybe if you're at your desk right now and you can take a look. Event producers in this new architecture, they fed directly into Kafka. So they took out this thing called Chukwa that was this event collection platform, and they just decided to have Kafka front everything. So you write all your events to Kafka. And in this episode, we get into why Netflix started doing that. And then Kafka interacts with a routing service that controls the job creation, whether that's a streaming job or a batch job like they originally had Chukwa feeding into. So yeah, we get into all this, like how this last data pipeline works. And we also talk about Elasticsearch and different streaming platforms. So anyway, with that introduction, I want to get into this episode. Thanks for listening to the show, by the way. And if you enjoy the show, please share it on Twitter or Facebook and tell your friends. That translates directly to growth and profit for our show. And as these profits grow, this becomes a increasingly viable lifestyle business for me to continue doing all these podcasts and also profit to reinvest into the company. I guess that's considered revenue more accurately, which I really want to do. I want to reinvest into the show and continue it growing. So you can help keep that flywheel spinning if you share with your friends and help us grow. But, obviously only share if you think they'll be interested. I don't want to be forcing you to, make types of sharing that you know feels uncomfortable to you. So, but anyway, thanks for listening to the show. Now let's get on with the show. Software engineers never stop learning. If you are listening to Software Engineering Daily right now, you enjoy learning so much that you listen to a podcast about technical software topics. IT Pro TV has videos for people like us, people who never stop learning. I'm using IT Pro TV right now to learn about Amazon Web Services, and I found 10 hours of high-quality videos about EC2, elastic load balancers, orchestration, cost management. If I ever decide to start my own tech company, I will need to know how to manage the cost of my servers. Go to itpro.tv/sedaily to get started with a free 7-day trial of videos. You can then use the promo code SEDaily and get a 30% discount, and that discount is permanent. Watching these videos, I have learned how to configure auto-scaling groups together with load balancers. I've learned how to configure a database that can scale up without inconsistencies. If I wanted to test out of the Amazon SysOps certification right now, I could. There are also courses about Microsoft operating systems and networking, VMware virtualization, Cisco routing. You can watch 70 hours about Cisco routing and switching, and it is engaging and entertaining material. If you listen to Software Engineering Daily all the time, this is the kind of material that you will love. You can put it on in the background, and you will find yourself just absorbing the information without even realizing it. You can try it free for 7 days. Go to itpro.tv/sedaily. Use the promo code SEDaily to get 30% off, and after you try it free for 7 days, I have no doubt that you will want to continue to invest in yourself and your future. Thanks to IT Pro TV for sponsoring Software Engineering Daily and for producing this top quality content. Stephen Wu is a platform engineer at Netflix. Stephen, welcome to Software Engineering Daily.
Glad to be here. Thank you for inviting me.
Today we are going to talk about the Netflix Keystone data pipeline. But before we get into that, let's talk more abstractly. Define what the term data pipeline means.
All right. So data pipeline for us means that the transfer data from the event producer to data consumption platform, for example, Hive or Hadoop. And also, we also can transfer data to Elasticsearch, where people can just do real-time index query. Or we can transfer data to like a Kafka, where people can run stream processing job. So basically, we're responsible to transfer data from source to the destination for people to consume the data.
And at Netflix, what are the types of data that are coming through that pipeline?
So I think we have all kinds of data from, let's say, user streaming activity. For example, when you play the video, we have like an event say, hey, you start playing video, you pause, you fast forward or move backward, all those kind of user activity. And there also can be like a performance metrics, for example, latency and call graph. It can also be like a troubleshooting data. Like, for example, when you write a system, you write some troubleshooting events. In case you want to debug some user problem, you can query the data to see what happened. Also, including application log, like error log, you write to when there's a log error in the application log file, we collect those and also send through a pipeline, and then we can even send to Elasticsearch. You can do a summary, and also people can query for those logs. So yeah, all kinds of data.
The data that enters the pipeline is event data. Can you explain what defines an event and how is an event formatted?
Good question. So basically, the data through our data pipeline is a kind of structured data. You have, although we don't enforce the schema, but most data is a structured data. For example, let's say take example of when you play the video, we may have an event. Let's say, hey, user ID is 123, username is Stephen Wu. Which the movie that I played, for example, is let's say Shawshank Redemption, or all those kind of structured events where you have field that define.
Okay, and so the data pipeline is responsible for collecting and aggregating and processing and moving around all the data for these events. And almost every application at Netflix uses the data pipeline. The Keystone data pipeline went live in 2015. but there's been a data pipeline for a long time. What did the data pipeline look like before the Keystone data pipeline?
Yeah, that's a good question. So actually, before that, I also want to clarify your previous question about what flows through our data pipeline. So one thing that doesn't flow through our data pipeline is a metric system. So in Netflix, traditionally, the business event and the metric system are two separate systems. So our metric flows through our what we call the Atlas, which is also open source. So those numeric metrics doesn't flow our data pipeline. So back to your question about what existed before our Keystone. So Netflix data pipeline experienced like a few major evolution in the last few years. At the beginning, our data pipeline is called the Chakra pipeline, which is the Apache project. So the Chakra pipeline at that time is very simple. We just, from the event producer, they send data to Chakra. Chakra then collect them, aggregate them, then upload the data to Hive. So that's it. That's all the data pipeline we have. So all our data analytic tool is in Hadoop or Hive query. So that's what we had before. So over the last few years, with the emergence of like Kafka and Elasticsearch, there's a growing demand of real-time analytics. So because in Hadoop is batch processing, people run their data analytic job every hour or every day. So with those like Kafka and Elasticsearch, people starting to wonder, can I get more real time? So that's why we started from Chakra. We started T-traffic to a real-time branch, which is powered by Kafka. And then we run our routing service, take data from Kafka to Elasticsearch. Or people can just run stream processing to the Kafka in the real-time branch. So we call that Chakra 1.0. That Chakra with real-time branch 1.5. So now our Keystone is a 2.0. Basically, we have everything is powered by Kafka in the front.
Right. So like you said, the original data pipeline was basically for aggregating and uploading these events just for Hadoop batch processing. And that data pipeline was pretty straightforward. The events got collected and written to S3, and Hadoop jobs ran over them. And obviously, like you said, there's the real-time increase in use cases that you had that led to the migration of the 2.0 data pipeline. But aside from the real-time augmentation that you added, were there any problems with the original data pipeline?
That's a good question. So that's a couple of additional motivation for us to make the architecture change. One is that the Chakra pipeline doesn't have replication. So if we lose the node and the data haven't been uploaded to S3, the data is lost. So it doesn't have replication. And second motivation is that when we have the real-time branch and the Chakra system, our architecture gets pretty complicated. We have a lot of moving pieces that make it complicated to maintain and to support because there's just so many more components to involve. With the Keystone, we just have two pieces. One is Kafka in the front. Second piece is our routing service. Basically, take the data from the fronting Kafka and write them to the destination, which could be a Hive, could be Elasticsearch, or there could be another Kafka. So we try to simplify our architecture also.
Okay, great. So let's start to talk about that real-time augmentation. Over time, there was this increased demand for real-time analytics at Netflix. Real-time, in this case, means less than a minute. So something happens, and then you want feedback on that event in less than a minute. What is a use case where this type of real-time analytics would be needed at Netflix?
Okay, yeah, good question. For example, when user calls our like customer support, say, hey, I cannot play a video. So then we have have a tool which will say, hey, which video this user played before and what's the error code. So those data, if we put in Hive to get that user information about the particular user is very, very, very slow because you need to basically scan the whole hour of data if you know which hour that the user views the video, which is very slow. But if we put the data into Elasticsearch, that pinpoint query is very fast. We can just, within a second, we can just get the viewing activity for a particular user. That can make then the customer service can just look into the viewing and it can help us troubleshooting much faster.
Sure.
That's one example. Yeah.
Right. Okay. Sure. And there's plenty other real time use cases. I'm sure. But so the initial way that you got real-time going was you augmented that original Chakwa pipeline. So what were the augmentations? So the original pipeline, just for listeners who don't really know, is like event producers feed into Chakwa, which is, I guess, this kind of event store, and then it gets stored in S3, and then MapReduce jobs, Hadoop jobs can run over S3. And then you augmented this pipeline with a pipeline that would allow for the real-time functionality. So what was the augmentation to that original Chakwa pipeline?
So basically in the Chakwa, in addition to upload data to S3, we also teed the traffic to a Kafka, which is basically the real-time branch. We basically teed the traffic to Kafka. Then go from there, we build up the routing service, take from Kafka and feed to Elasticsearch, or then people can run stream processing on top of the Kafka.
Right. So what were the kinds of applications? I mean, so the real-time added functionality that you gave to the old pipeline, you sent event data from Chakwa to Kafka. So you forked it, like you said, and then Kafka would send that data to Spark consumers or to other consumers that were reading off of that Kafka stream, whether it was to the router that went to Elasticsearch or just Kafka feeding directly into stream consumers like Spark. So what were the kinds of applications that were starting to consume this real-time data off of Kafka using Spark or Mantis or any of these other streaming consumers?
Oh, that's a good question. So, for example, our security team, they run a Spark job to consume from the Kafka to do the distributed enough service attack detection. So they need real time to train their model and to react fast. That's one example.
Okay, all right, sure. And what about the Elasticsearch? Because you also got Elasticsearch out of this real-time augmentation. Mm-hmm. What do you use Elasticsearch for?
Oh, so Elasticsearch actually has been tremendous popular in Netflix. So I think right now we have probably more than 3,000 Elasticsearch nodes deployed in Netflix. I gave you an example before is that basically people want the data in Elasticsearch so they can do a fast query of the data. Instead of Hive, you have to scan a whole hour of data to Elasticsearch because indexing capability, you can just do a very fast, hey, I want this information. Mm-hmm. Elasticsearch can respond to you much quicker.
Okay, so the fast querying is allowed because Elasticsearch just indexes everything as soon as it comes in.
Yes, exactly. So that's why it becomes so popular. People can get the response very quickly in terms of a few seconds.
And very interesting. I feel like Elasticsearch has really grown in popularity over the last maybe 2 or 3 years. Do you think that's accurate?
Yes, I think in Netflix it'd be tremendously popular. We have, as I said, 3,000 Elasticsearch cluster, Elasticsearch node deployed in AWS and probably dozens of clusters.
Why has it gotten so popular in more recent years?
I think just because they get what they want fast.
Yeah.
Instead, you scan the data.
Was there something that was preventing it from getting popular before then? Because, I mean, getting data fast because I've indexed it seems like something I would have wanted even 3 years ago.
Well, I think Elasticsearch, they really become mature probably just 3 years ago. That's what my understanding. They really start to take off and become feature-wise, stability-wise, scalability. They really become mature, I think, started from 3 years ago.
Okay. So like you said, off of Chakwa, you had this Kafka cluster, and then that fed into the stream consumers. Then it also fed into this routing service, and the routing service would feed into Elasticsearch. So what is the responsibility of that routing service?
So the reason we first of all teed the traffic to Kafka, because that kind of give us a buffer. So in case, let's say Elasticsearch is down, we have the data can buffer in Kafka. Because Chakwa is a stateless, it doesn't buffer anything. It get data, it just push the data out as fast as possible. So Kafka gives us the buffer. Then our routing service, instead from from Chakwa, you feed to Elasticsearch directly. So the downside is that if Elasticsearch is down, then you have no way to put the data to Elasticsearch. But with the Kafka, if Elasticsearch is down, let's say for maintenance purpose, Kafka can give us a buffer that we can still replay the data, feed the data into Elasticsearch when it's back. So our routing service basically in the middle is basically consume data from Kafka and then produce the data to a particular data sink, which can be Elasticsearch, can be Kafka, another Kafka. So basically it's a kind of like a data relay service.
Right. Okay. So what were the problems with that routing service?
So in our the 1.5, the Chakra with Kafka real-time branch, we implement our own routing service. Basically, it's using the Kafka high-level consumer, and then we build like a kind of custom application. So there's a couple of problems with this approach. One is that, first of all, the Kafka 08 high-level consumer uses Zookeeper to do the coordination, to do the partition assignment. It's not as stable as we want. Sometimes the routing service is running fine for a few days, and suddenly they get in a state that it just doesn't consume anything, or it just doesn't consume some partition. So the stability of the 08 consumer is not as stable as we want. Second is because our routing job, we have like hundreds of routing jobs, and we manually manage them by creating like dozens of clusters, and each cluster, for example, take maybe like 10, 8 routing jobs. So that management of that hundreds of routing jobs manually and using the traditional app, it's become very cumbersome. It's create a lot of overhead for us in terms of operations.
Mm-hmm. Eventually, you decided to revamp that entire data pipeline architecture into a Kafka-fronted architecture. So instead of this 1.5 version where events were being collected into Chakra, they would go straight into Kafka. So the ingestion layer was Kafka rather than Chakra. Why did you decide to do that?
Yeah, so that's exactly what's happening, because we want to get rid of Chakra because that's one less system to maintain. And also, Chakra is not really taking off in the open source community. Not many people are using, and Kafka has a strong momentum and have a very vibrant community. So we like to just on board to that momentum and to get on with that the open source product that everybody likes to use. And so get rid of Chakra functionality wise. Both Chakra and Kafka has some overlap. Not exactly the same, but they have some overlap. So we can achieve what we do just with Kafka we can get rid of one component to maintain. So that's one big reason, just to simplify the architecture and get rid of the one thing. Yeah.
So it is so interesting how much momentum Kafka has gathered over recent years. And it also seems like one of the few areas of the Hadoop ecosystem. Well, it seems like one of the few areas of the Hadoop ecosystem where there's really been a lot of consolidation. Just people are using Kafka for its use case. Why do you think Kafka was so successful over the other queuing systems?
That's a good question. I think performance is a key because it doesn't have a lot of feature. It's kind of just a transaction. It's just a log service. So it's very simple and it's very fast. I think that's the big reason. For example, in Netflix, we transfer, let's say, over 1 petabyte of data every day. So performance is very critical. So Kafka is very high performance. And second, I think it does support the critical feature of PubSub, which is important for us because the same data topic, we can have multiple routing jobs to consume from the same topic. So that the PubSub is also very important for people. And it also, if you talk about using Kafka as a message queue, it does give you the ordering when the data is in the same partition. So I think the right balance of performance and feature-wise, I think make it pretty attractive. It's not too complicated to make it slow, but it's also good enough to satisfy a lot of use cases.
Right. And in this particular use case, Kafka also has replication. So that gave you some durability that you did not necessarily have at the Chakra event ingestion version in the 1.5 or the 1.0 version of the data pipeline. Explain how the replication of Kafka improved things at the ingestion layer.
Yeah, I think that's a very good point. So we actually started using Kafka 0.7, which doesn't have a replication. So at that time, we only use the Kafka in the real-time branch, which is like kind of, I won't say the toy system, but it's kind of non-production quality. People can just play with it. Since they introduced the replication in 08, that's when we start to consider, hey, is Kafka ready to take over our entire pipeline? So yeah, so support of replication is definitely a deciding factor for us to move to Kafka.
Okay, great. Software engineers are always looking to automate their work. Software automation lets us get more done with the same number of resources. Investment automation works the same way. Wealthfront is an automated investment service that relies solely on software to acquire and manage client accounts. Traditional investment services have many humans in the loop, advising clients and taking fees. The problem with these older advisory services is that the advice that these services are applying is often so systematic that a computer could give the same answer, or an even better answer. Wealthfront takes a new approach with software-driven automated investment that provides better returns through software engineering. Go to wealthfront.com/SE daily to get a special offer for our listeners. $15,000 managed for free when you open your account. Don't pay commissions and account fees. Maximize your gains with Wealthfront's Set It and Forget It investment automation. Check out wealthfront.com/SE daily. It would support Software Engineering Daily, and it would also introduce you to the world of automated investment, so you can see if you like it or not. Wealthfront.com/SE daily. Thanks to Wealthfront for sponsoring the show. You've been a loyal sponsor, and we really appreciate it. Now let's get on with the show. So the new architecture of Keystone, it has all of the event producers writing into Kafka, like we said, in the 2.0 version. And Kafka sits in something called the control plane. In the control plane, Kafka interacts with that routing service. So give me an idea of what the purpose of the control plane is.
Okay. So our main system is Kafka is for injection and routing service. We run our routing service. I probably haven't mentioned this earlier. So we implement our routing service using Samsa on top of a Docker container. So the control plane is basically a routing job manager, which kind of deploys the Docker container in our computing resource. So our by control plane, we mean those job management. It's not about the Kafka and the router as a control plane. It's just control plane is about managing those routing jobs.
Yeah. Okay, so the control plane is useful for data ingestion and data buffering and data routing. Let's go through each of these. The Kafka ingestion layer of Keystone has two ways of writing data to Kafka at the entry point. You can use a Java library to write directly to Kafka, or you can send an HTTP proxy that then writes to Kafka. Why is it useful to have two different ways of ingesting events in Kafka?
So traditionally, Netflix is a Java shop. Almost every application is written in Java. So since last 1 or 2 years, there started being more polyglot system. Some application is written in Python. Some application is written in Node.js. So for us to maintain a library in every language, it's become too much to handle. So we just decide to support a REST endpoint, because any language have very good support to REST service. So we just decide, hey, I deploy a REST endpoint. You can publish your data to that REST endpoint. So that's our way kind of support a polyglot system environment.
So Kafka is useful as a data buffer, and Kafka can also help deal with downstream outages. Explain why Kafka adds some resilience against these types of outages.
That's a good question. So I think from time to time, we have experienced S3 outage. For example, for let's say a few hours, S3 just is very slow, or it's even complete outage. If that happens, if we have the Kafka as a buffer, during those few hours, we have data buffered in Kafka. So when the S3 come back, we can still consume the data from Kafka and upload them to S3. So that's what we mean by we can absorb the outage. What happen more often is Elasticsearch. For example, we have very big Elasticsearch deployment. Sometimes if the Elasticsearch is under provision and it becomes slow, or sometimes they want to do maintenance. They want to shut down the Elasticsearch and bring them back again. So with the Kafka in the front, we can absorb those kind of transient problem without losing any data.
So what's the retention policy for your Kafka messages?
Depending on the priority of the data, we usually for like a regular priority, normal priority, we keep the retention at 8 hours. For high priority, we keep data at 24 hours.
Okay. So from the control plane, data can be routed to the S3 Hadoop MapReduce channel, or data can be sent to Elasticsearch, or data can be sent to a different Kafka stream, which feeds streaming consumers like Spark. And this method of routing, like you said, uses Samsa on top of a Docker container and MySQL. So explain how this works.
So first of all, by control plane, I didn't mean a Kafka or the routing service. By control plane, I mean that it's managing those routing jobs. So it's not about the Kafka or routing service itself.
Okay.
It's the coordination manager of those routing jobs.
Oh, okay. Okay, interesting. So can you tell me how that works, how that job management service works?
Okay, so when we first started, we were hoping to run our Docker container on top of our internal container service called Titan. Right now it's renamed called Titus. So, but when we started, with the Titan project started a little bit before us, but when we are ready to go, they are not as stable as what we want. So what we did is that instead of rely on Titan to do the more sophisticated resource management, rebalance, we just implement our own simple way of routing assignment. Basically, we have a routing manager, just look at the traffic and calculate, okay, per container, how many partition can each container handle based on traffic volume. Then we assign the job statically to an instance. So we have a relative static assignment. So it's everything relative static is not as efficient or as dynamic as what we want. So right now we're working with, but when we started, it's not ready. So right now we're working with our Titus team to think about how to migrate to their platform. Then that will remove us from a lot of those management work. So basically we want to migrate our routing service on top of the Titus framework.
Can you explain why you would use Samsa for the routing service?
So when we first started evaluating the stream process, that title of my previous comment about, in our previous routing job, we write our own custom application. We manually assign them using config file. That become very high overhead into management. So we want to use some more container job and then run it on top of some container service that can make our job management much easier.
Okay. So was there anything particular about Samsa that made it well suited for this job?
Yeah, so evaluated the stream processing system at that time. We compared Samsa with Spark. So at that time, I think that's in probably April 2015. At that time, Spark doesn't have backpatch handling. Means that when you write to a destination, cannot keep up. They will just drop the data. There's no backpatch handling, all those things. At that time also, when we do performance testing, Samsa is much more high performance compared to Spark. Obviously, over last year or so, Spark made a lot of progress, but at that time, Spark is just not ready.
Okay, I see. So could you talk in more detail about how you use Docker and why do you spin up a new container for each job?
So because each of our routing jobs, we assign, for example, we basically want to, container can give us a good job management capability. Instead of our manually assign the thing to a particular instance, we just, hey, here is one job which handle 100 megabytes of data, and we give it one CPU. So those make our job management so much easier and clean. We just say, hey, here's the resource we want for this job, and then you figure out the assignment.
Mm-hmm. Yeah, that makes sense. Okay, so the stream processing at Netflix, one of the, like you said, one of the consumers of the Kafka ingestion layer and the routing service and the control plane, one of the ingestion layers is these stream consumers like Spark and Mantis and other applications. Could you talk about Spark versus Mantis? I actually have never heard of Mantis, but I'd love to know about these two different ways of consuming data and doing stream processing.
Sure. Actually, stream processing in general is a very young field. There's a lot of new systems come up every year. For example, right now, we're actually evaluating Flink, Apache Flink. So, but Mantis, just give a couple more words about Mantis. Mantis is a stream processing framework that built in Netflix internally. It's primarily used by our Edge team for operation insight to say, hey, do we have like a stream outage? Is any like a, they use it to detect is any title have like a playback problem? People cannot play a particular movie or particular TV series. So they use that to detect all those kind of things. So I don't think it's open source yet. I think that the Edge team did give some talk in QCon or those kind of conferences, but I don't think it's open source. It's just another stream processing framework built on top of RxJava, the reactive framework. So yeah, it's just yet another stream processing framework.
Why are there so many of these? Like, okay, you're evaluating Flink. That's great. And all of a sudden now Apache Apex has come out recently, I saw, and I should probably do a show on that. But what's your perspective on why there are so many of these stream processing frameworks?
From my point of view, I think it's just because it's so young. It's a young area. No player has said, hey, I have everything everybody needs. Mm-hmm. For example, in Mantis, the reason we started is because none of the stream processing framework outside there have auto scaling. So for the Mantis, they build auto scaling in the AWS. So that is very important for them. That can save a lot of money. So just from different perspective, since like Samsa, when they started, they tied very closely with Kafka. So when they start, they have pretty good integration with Kafka and more stable. So yeah, I think just because it's a new area, that different people come from different perspective, they kind of focus on different area. Hopefully within a year or so, there's one or two will emerge as a kind of dominance and everybody can just get on with it.
Wasn't that just supposed to be Spark?
I don't know. I think right now, well, we'll see. I think I cannot make the prediction. We'll see how things shake out.
What's appealing about Flink when you guys are looking at it?
I think the thing appealing to us is that Flink has I don't know if you heard about Apache Beam or no, which is a Google data flow. It's a stream processing API. So we kind of like the idea have a Beam as an API layer. Then we can, underneath, we can run the stream processing over any system, for example, Flink or Mantis. So we kind of like that abstraction of Beam. And Apache Flink have the better support the Beam API as far as we know. So I think that's one of the reasons. And also it actually have a pretty good company behind it. So just like Kafka, they have a conference behind it. So a good company and the foundation behind the framework is kind of can go a long way.
Absolutely. Could you talk more about that Beam API?
So Beam API is so Google have the paper called the data flow, which describe how they do the stream processing in Google. And Beam is an open source project that Google started to define the stream processing, kind of just abstract API layer. It's just an abstraction. It doesn't determine how you run the job.
Okay. I get it.
So you can run the Beam over Flink runner. You can run the Beam over, let's say, Spark runner or Mantis runner if you want.
What is the abstraction that it presents that's so flexible that it can be consumed by Spark or Flink or any of these things?
So I'm not very familiar with that.
Okay.
In terms of API-wise, but I think it have all the window. It also have a distinct definition of event time and processing time, but I'm not very familiar with all those details.
So when you look at these different stream processing frameworks, when you're looking at them from the point of view of being at Netflix, I imagine that there are unique stream processing needs at Netflix. And I'm curious how that matches up with the different stream processing tools that are available. So could you give me some color on that? Like, what are the unique stream processing needs at Netflix, and how do those match up against particular stream processing tools?
So that's a good question. So take an example. Our routing service right now uses Samsa stream processing. But for our routing service, we don't need, it's actually pretty simple thing. It get the data in, maybe do some filtering, transformation, projection, then writes data out. It doesn't do like machine learning, doesn't do all those statistical calculations. So for that, like routing service, we need something stream processing that high performance, have back pressure. Those are important things for us. On the other hand, for example, if you are a data scientist, Spark might give you this like machine learning integration support that Mantis doesn't have, for example. So, or like for us, we don't care, like for our routing service, we don't care about machine learning support. We don't need it. So it just depends on your use case. In Netflix, yeah, we run stream processing as a simple routing service. Some data scientists, they run Spark job to do machine learning, and or like a security team, they run Spark job to do the anomaly detection for the DDoS attack. So yeah, depends on your requirement. You may care about different things for stream processing features.
It's very interesting. So I know you said you think that maybe there'll be one or two that kind of win out, but do you think that there's maybe a potential future where it's like stream processing layers are like the new database, where like, you have Cassandra that's useful in some situations, or Mongo in some situations, MySQL in some situations. There's no one size fits all, right? Like, do you think that could be the case with streaming?
Yeah, I think that could be. I think you probably won't have one thing that take off, but you probably will maybe have two or three, for example, it become really popular. But it won't. I think today you probably have, 6, 7, 8, probably, and more maybe come out. Who knows?
Okay, so let's talk about monitoring. How do you monitor the data pipeline at Netflix?
So that's a good question. So as I mentioned earlier, our metric system doesn't follow our data pipeline. So we rely on Atlas, which is our metric system, to do monitoring. So we report metrics, and that doesn't go to our pipeline. So it's a separate system. So that's how we publish metric. We set up alerting. We also use Winston, which is our internal automation framework. We try to automate like alert handling. For example, when we have alert, hey, you have disk failure. So we can automate we don't have the manual to do anything. In our alert action, we can say, hey, just terminate the instance automatically. So that can reduce a lot of our manual work in terms of monitoring operation. So yeah, so metrics is the key. We have to have good set of metrics and set up proper alert and automation.
So yeah, this automation engine called Winston that handles the monitoring and alerting and actually takes action on those alerts. This sounds like the no-ops philosophy that I've read about associated with Netflix. Would you say it's an accurate characterization?
Yes. So, but we are not complete no-op yet. There's still some thing we still do manually, but we're trying to get more and more. But we need to kind of, first of all, we have to have confidence that automated action is the proper thing. Sometimes we may need, but still we're not confident. Hey, is that always right? If we're not totally sure, we'll still get human involved. But human involved always have a higher latency.
Certainly. And how does that... So when you do something huge like migrate the entire data pipeline to a new version, I imagine that you want to have a significant amount of human supervision over the updated system after you change to the system. So how does that process of moving from a highly human-controlled system, how do you go from that to an increasingly automated system?
So if you're asking about the migration from Chakra to Keystone, is that the question?
Yeah, well, it was a bad question. It was a poorly formed question, but I'm just saying, like, when you migrate something that's so big, that has such a significant effect on the infrastructure, and sure, you want to have this no-ops philosophy, but it seems like if you do something that the integrity of the platform is so dependent on, it seems like you would want a lot of manual oversight in place, at least at first. Obviously, you want some automation, but you want a lot of automation and you want a lot of manual oversight. And then it seems like gradually you would want to have less humans in the loop and increasingly automate those humans. I don't know, maybe you could just tell me about the procedure of setting up the automation around the Keystone pipeline.
Sure. So I think let me talk about the migration. Actually, so when we migrate Chakra to Keystone, it's not like a one day we just we flip switch. So what we actually did is from producer, we do the shadowing. Basically, we write same traffic to the old pipeline, Chakra pipeline, and to the Keystone pipeline. So we run both pipelines at the same time, and then we write the data to the Hive. So we have both Hive run available. We have our production Hive, and then we have our shadow Hive. So after we have both pipelines running, we also do the data comparison. So make sure the data, they're identical in the Hive table, in the production Hive and the shadow Hive. So we do the shadowing and do the data validation. After we run those dual pipeline for a month, and we iron out all the bugs, issues with the data quality thing, then a month later, that's when we did a switch. So actually, I can tell you a good story. When 2 days after we switched to Keystone, we had a big outage, which lasted for 10 hours. The fortunate thing is that we still have a Chakra pipeline running. So at that time, we just switched we basically just restore the data from the Chakra pipeline. So we don't lose anything. Unfortunate things happen is because it just happened 2 days after the cutover. So that was the best thing.
So can you tell me more about the automation, though? I know I asked that question really poorly, but tell me what kinds of automation hooks you would put in place around Keystone to handle failures. For example, you monitor the Kafka brokers and the Kafka consumers in detail. Talk about how you set up automation around those Kafka brokers and consumers.
So basically, it's just like a matrix. We like a Apache metric for each broker. They can find out how many partitions is out of sync for that broker. We publish those metrics. We can also publish, let's say, disk utilization, CPU utilization, all those important things. Then we basically set up a alerting based on threshold.
Okay, that makes sense.
And then we can, that's first is detecting things happen. Then it's a handling of the problem. Handling of the problem, we can page it on call, which can manually handle it. Or if we know, for human, when we get a page, usually go through a few diagnostic steps. Hey, is this happening? No. How about this? No. Next one. So you usually have a kind of run book type of step you normally follow. If that step is well defined, and then we try to scriptize it, and then automate that handling using a script. If something that script can handle, then we probably just raise it to the uncle. Hey, I don't know what's happening. Take a look.
Okay, that makes a lot of sense. So you start off with, you have an ops guy who's overseeing, or guy or girl who's overseeing the troubleshooting process, and then over time, the ops person writes down what's going on or the procedure for handling a problem. And then once you have the human procedure written down, it becomes easy to script that and automate it and put it into code. And then you can always escalate after running those well-defined checks, escalate it back to the ops person if those don't work.
Exactly. So basically we learn, then we scriptize, then we improve.
Fascinating. So I'm sure that the Netflix team was looking at cost management when building Keystone. What are the types of infrastructure decisions that were made around managing cost?
So that's a very good question. So I think the key thing for us, for our team, is give the user the visibility. For example, I think starting from January this year, we started to tell team or other engineer team, hey, you send so much data to our data pipeline, that is equivalent to the amount of dollar every year. So after we expose that visibility, people, they send our data, they don't know how much it costs. They have no idea. They say, hey, I give it to you, you deliver, great. But as an infrastructure, we handle 1 petabyte of data every day. So that's a huge infrastructure. It's a very high cost system. And after we did the cost attribution to the engineer team, then they start to realize how expensive it is. They start to optimization. So immediately after the new year, we actually reached 1 trillion events per day. And after we did the cost attribution, give the visibility to the engineer team, they start to realize how expensive it is. They did the optimization. For one example is that one team, they send 4 million events per second to us, which is one of the most, it's a heaviest traffic in terms of message per second. So after we exposed that cost to them, they did the optimization, start to batch in the events. They reduced the number of messages from 4 million to less than 100,000 less than 100K per second. That's a few hundred X of reduction in terms of number of messages. Yeah, so the visibility exposure is a key. In Netflix, we don't try to dictate, hey, you can only spend so much money. We don't do that, but we give you the visibility, give you the tool. Then they can make the decision themselves. Do they want to spend their resource to optimize this, or they think, hey, I have more important things to do. We don't dictate people what to do, but we do try to give people the tool and the visibility.
That makes a lot of sense. You just display the P&L to each of these well-defined teams at Netflix, since Netflix does have well-defined small teams, as I understand.
Yes.
And they see their P&L, and they can choose to audit themselves when they want to.
So we always promote freedom and responsibility. So each engineer team have the freedom, but they also have the responsibility. We hire mature engineers; they all make kind of a reasonable trade-off decision, but we don't dictate. We try to provide the context for people.
Let's zoom out. What is the developer experience like for interacting with Keystone? Is it like self-service, or do I need to contact the Keystone team to help me get set up if I'm a team in Netflix?
That's a very good question. So when we first started, we let the contact is a spreadsheet. People fill in a row in the spreadsheet. Hey, I want to send data to this topic, and this is my traffic estimation. Then we manually provision that. We're working on a self-serving model, so we can build the UI. People can just go there, provision their stream based on their traffic. Yes, so we definitely want to go to self-serving. That is our manually provision of those stream is a big burden for us. Our on-call has to spend a lot of time to manually provision those data stream and all the infrastructure. So yes, self-serving tool is something we want to automate that. So that's definitely something we want to do. We're not there yet. We are started. We already make a few baby steps, but hopefully by end of this year, we can make it fully automated and self-serving.
Okay, wonderful. So what is in the future for the Netflix data pipeline?
That's a good question. I think we touched on a couple of things earlier. One is that self-serving that you just asked earlier. We want to move from manual provision the model to self-serving model. So that can relieve us to a lot of manual work. Second is something you mentioned about automation. So we did a lot of automation, but our ultimate goal is, I won't say 100%, but close to 100% automation. So that needs to build a lot of intelligence in our control plane. We need to, not scripting may not be enough. We may need to write some, I won't say it's AI, but we need to be more sophisticated than scripting and more intelligent and more. So that's something we will invest heavily in the next year or so, try to relieve us from all the manual work. Third thing we're trying to look into is stream processing. So once we have the pipeline that the front end by Kafka, so that's a growing demand of stream processing in Netflix. People have been doing their own. They have been running their own Spark job. They have running their own Mantis job. So from our data pipeline point of view, we're trying to build a common framework so that the people don't have to run those systems themselves. We run the infrastructure for people. People can just write their stream processing job on top of our platform. For example, using the Apache Beam API. Underneath, it can be Mantis, can be Flink, can be anything. For example, maybe 2 years down the road or 1 year later, that's super awesome stream processing framework come out. Then we can just switch that and people don't have to. So we try to build up that stream processing platform inside Netflix.
That's great. Okay, cool. Well, Stephen, thanks for coming on this show. This has been a really great conversation. I really enjoyed talking to you.
Sure. Thank you for having me.